This video will continue our discussion of section 14.3. This is double integrals and finding volume of a region. So of an area. Area is the wrong word. Volume of a space, I guess, or container, or something like that. So find the volume below of of that function. So we have some kind of function. We don't even have to try to draw the z function. Above the xy plane, that's what we have drawn on there. Between these two things, these are circles. This is a circle with R1. This is a circle with radical 2, R radical 2, right? Remember, it's x squared plus r squared. X squared plus y squared equals r squared, which means we would need a rad 2 there, not a 2. It's a very common mistake. So I get this circle. Do the best we can. Then we also have a circle with radical 2. I'm just going to put it somewhere between 1 and 2. So the region that we're actually trying to find the area or volume above is this donut looking section. So I'll fill this in real quick. We are finding the volume above that region. So we have some kind of surface that lives above this coordinate plane. It's like it's coming out at you, or I'm looking at an iPad on a table. The z-axis would be going up and down if this was flat. But it's coming out you of your computer or phone screen. We can pick up some other things. Let's pick up some R equations. Okay, so x squared plus y squared equals 1. Well, that's r squared equals 1, which is r equals 1. Well, we already knew that. We picked that up there, so you could get it from either place. We also have this. This was 2, so that gives me r squared equals 2, and this makes maybe a little more obvious for you. If I take the square root of both sides, on that side I get radical 2. All right, I think I have enough to build my volume integral. I know that theta always goes on the outside every single time, and it's a whole ring, so 0 to 2 pi. And then our r's are going to go from the smaller one, 1, to the bigger one, rad 2. You could use your calculator if you were unsure. A couple of things we didn't write down, but it's always true. X equals r cosine theta. Y equals r sine theta. So we can plug this into our surface now. So on top we get r squared, because it was a y squared. That's what we're looking at. It's an r squared sine squared theta. We just squared both of them. On the bottom, an x squared is going to be r squared cosine squared theta plus r squared sine squared theta d theta. We got to add everything else in though. Okay, theta, then r dr d theta. Do not forget the r. It's very easy to forget. I almost forgot the whole back half of it. So, okay, we can rewrite this. Let's go ahead and do that. I'm not changing any bounds, so I'm going to be lazy and not write it there. I get r squared sine squared theta. Then r squared's in both of these, so I'm going to factor out that cosine squared theta plus sine squared theta. And r dr d theta. All right, so now I'm going to write my bounds because it's going to look closer to my actual problem. I replaced everything. These r's are going to cancel. And then the cosine squared plus sine squared on the bottom will be a 1. And then I do have an r, so I have r sine squared theta dr d theta. All right, we are only integrating with respect to r. So we have theta from 0 to 2 pi still. But now we have r squared over 2 sine squared theta d theta. And we're running that from r equals 1 to r equals rad 2. All right, we can drop those because we're only going to have thetas now. All right, so we get, if I plug in root 2 squared is 2 over 2, so I get sine squared theta minus, and then I plug a 1 in, I get 1/2 sine squared theta d theta. That's plugging into my r bounds. I still can go further, even though you may not think or see it. I have 1 of sine squareds minus 1/2 of sine squareds gives me 1/2 sine squared. Right, we're going to use another identity here, a trig identity. So it's going to be 0, 2 pi. And what we're going to do is replace sine squared with a trig identity. We used this recently, a different one related to cosine, but this one goes cosine 2 theta plus 1 over 2 d theta. So that's a trig identity. These ones that show up in homework, if it were me and I was in your boat, any kind of trig subs, if I don't do it in a video or do it in a homework, I really wouldn't expect it to show up on an assessment. So if you find some in the videos or homeworks that you don't have down or memorized and you need to write it down, that could be something if you're allowed a note card, if you're allowed a piece of paper, depending on which course you're in and what I'm doing that semester. But even in your studying, if you don't get a sheet of paper and you know these trig expressions are the ones that you always forget, what you do is you memorize it. You're looking at a piece of paper right before you go in to take your test. You put it up, and then when they hand you the test, the first thing you write down are those things that you forget all the time. Little trick for testing. Okay, I'll move forward. Some of you guys are like, yeah. But okay, so here, I'm going to rewrite this for a moment just to make things look prettier. D theta. There we go. Okay, we're going to do a U sub here. Yeah, we'll do that. U equals 2 theta. If you can do these without doing U sub, fantastic. Do it. If not, then maybe you shouldn't. Okay, so that 2, I put a half there and I was thinking ahead, but this becomes 2 d theta, which is 1/2 du d theta. So it means I have to introduce another 1/2 to my problem. So that's going to make that a 1/8 out here. I can plug my boundaries into there. So 0 for theta gets me a 0 for u. 2 pi for theta gets me a 4 pi for u. This becomes cosine of u plus 1 du. All right, so now we can actually integrate our last step. You could throw that in a calculator if you'd like to. So the derivative of cosine u is negative sine u plus u. And then we're going to run those bounds from 0 to 4 pi. So we get 1/8. I'm going to leave that out front of everything. Sine of 4 pi is a 0. So we get 4 pi, that's plugging into u here, minus, plugging in 0 for those, we get 0, and that's going to leave us with a pi over 2. So the volume of that surface caught in this region here, in that donut region, there's a surface on top of it. The volume between and that caught in there is pi over 2 units, whatever that may be in this case. All right, let's get one more example for this video. So it's the integral over y, the surface y, dA. The region is bound by x squared plus y squared equals 2x, and y equals x. Now, that first equation doesn't look like it, but it's a circle. I'm going to show you how to get to making it look like a circle. I'm going to minus 2x. Some of you guys are going to hate this. I'm going to put a space plus y squared, and then I have a 0 over here, and I'm going to put a space. We are going to do what's called completing the square. We take this, we divide it by 2, and then we square it. That's going to give me a negative 1 squared, which is a 1. So I'm going to add a 1 on this side and on this side. This gets me now, if we look here, this will factor to x minus 1 squared. Plus y squared equals 1. Now it looks like a circle. X something squared plus y squared equals a number that's not 0. So we know for sure that is a circle. And it's shifted on the x-axis right 1. So this circle, do my best to go through these 4 points. See if I do this, I wonder if it'll fix it for me. And then I wonder if I can make it work. You see it, there it is, it's good enough. We'll leave it there. Okay, so it's not too bad actually. So I have a circle, and then this is a line, we know that goes through this point, 1, 1. So this is also a a region that shows up a lot in calculus. You have seen it before. Talking about this region here. All right. So we're talking about a surface y, whatever that means in 3 dimensions. We could think about it, but let's just not get wrapped up in that yet. We want the volume of the surface on top of that, or below it, whatever it may be. Okay, this was going to be, it's tempting to do it in rectangular and set up that way. But the problem is that circle is going to cause some issues with this. Let's try it, since this is the polar section, in polar. Okay, so that means I need to change some of these things, and it's not as clear now. We have x squared plus y squared equals 2x. Now I can convert this to polar because the left side is r squared, and then what we can do with the right is, remember, x is r cosine theta. So I can just replace it there. Well, now if I divide by r on both sides, I get r equals 2 cosine theta. So that's the circle. That's what's going on there. So there's that, and then we have enough information, I believe, now. So the volume over that region, remember, thetas always go first. We know that the theta right down the middle is pi over 4. You just got to have that down. Right down the middle is pi over 4 from trig. This is also not a negative down here. It's just I accidentally hit that. I'm going to try to get that deleted. There we go. Okay, so pi over 4, and then straight up and down is pi over 2. And then, okay, r's. Well, if I start here at the origin and I go out towards, I'm already in the region. So it goes r equals 0 to r equals the circle, 2 cosine theta. The argument inside, if we look back at the problem, was just a y there. So this is just r sine theta, r dr. Don't forget the r. I got really sloppy there. R dr d theta. All right, so if I rewrite this, I get theta equals pi over 4. Theta equals pi over 2. Theta equals r equals 0, and r equals 2 cosine theta. Then we have r squared. We did all that just to put those two r's together. Dr d theta. All right, so now we can take our integral. I'm going to add a page here. One sec. Wrote a little too big. All right. All right. Yes, and we're ending this video after this problem. All right, now I can integrate. So theta is pi over 4, pi over 2. Those are our bounds. Then I get r cubed over 3 sine theta from 0, r equals 0. So r equals 2 cosine theta, d theta. We plug those in now. All right, so we get, I'm going to drop my labels because I'm not going to have any r's anymore. Okay, plugging that in. We plug in 2, that's going to be an 8 over 3 cosine cubed theta sine theta, minus, if r is 0, it's gone. Okay, that could have got even worse. It's not that bad right now. The u sub that's going to work for this is you do cosine theta. Du then would be negative sine theta, d theta. So I'm going to throw a negative out in front. I'm going to go ahead and change my bounds. Okay, cosine of pi over 4 is radical 2 over 2. Cosine of pi over 2 is 0. We can also pull out that 8/3. And then u is cosine, so that's u to the third. And then I already took care of the negative. The sign's replaced, and the d theta is replaced with du. Right, so we get now negative 8 over 3. 1 over 4 u4 from rad 2 over 2 to 0. Right, so we plug that in. We get negative 8 over 3 times 1 over 4 times rad 2 over 2 to the fourth. Minus, if I plug in, oh wait, we should have plugged in 0 first. So first one is 0. minus negative 8 over 3 times 1/4 times rad 2 over 2 to the 4th. The first term, that's all 0. The second term, once you work all that out, I believe you get 1 over 6. I think the 8's go away, and we get, oh, wait, one of those 2's, and then 2, yeah, I think it does work out to that, so give it a double check. If it's wrong, always email me, please.